Welcome back to another lecture of linear algebra. Let's go. On the last lecture, or the last past week, we've been working on linear accommodation, spans, and bases. And so now we're gonna still continue this momentum, well, of some of them. Well, actually, it'll be all of them. And we're going to discuss about change of bases and the Rank-Nullity Theorem. So let's get right to it. So before we discuss about change of bases, let's do a quick little review about bases, or a base. And so a basis is a set that's linearly independent and it spans an entire vector space. So the keywords are linearly independent and span an entire vector space. And it is also the minimum spanning set for the vector space, as I mentioned earlier. So for a two-dimensional plane, the minimum spanning set would be 2, which would be 1, 0, and 0, 1, or just like any combination. There can also be multiple bases in a single vector space. So that means that going back to the 2D plane, we have a bases 1, 0 and 0, 1, but we can also have another bases that could be 2, 3 and then 1, 7 or something like that, something along those lines. I think that might not be a basis. I could be wrong, but it's just like different ways of representing the same thing. And so there is a way to convert from one base to another. And so the way we're going to do it is, well, we're just going to start off with two bases, B and C. And so to go from one basis to another, well, in this case, to go from bases B given the base C, all we really have to do is just multiply the basis C by some matrix, which would be P B to C, and to switch back, it's pretty much the same thing. The only thing you're changing is you're going from B to C instead of C to B. And so a quick little detour, as you can see, you have like a little weird notation here with the B, or with the P, and then with the subscript going from B to going from C to B. And that's pretty much the notation of, these two can be represented as like two different things, but this notation, it means the same thing, which is the matrix that converts from one base to another. So you can think of it as a translator. So going back to the previous example, you have base C, and then he's going to talk to the translator that goes from C to B to give you B, and then vice versa. If B wants to, like, reply back or something, then it goes to another translator, which would be from B to C, so C can get the message. So that's one way you can think about it. And so you're probably asking why why this is important. To be fair, that's a very valid question. Like, bro, if you have a 2D plane where the base is 1, 0 and 0, 1, why would you think of something crazy and just change the entire base? Well, it can make things a lot more simpler. And to be honest, if you're in high school or in college and have taken a physics course, it is very common in physics, and you may not even know about it. You may not even realize that you've been doing it all your life, or all your career in your physics academic journey. So it's more, we can give you a common example when it comes with mechanics. So let's say we have a slab and boxes on top of it, and it's sliding down at some angle, and the slab, or the not the slab, the ram is at some angle theta, and it's sliding down, or block is sliding down. we have our xy coordinate here, so obviously we know that x is going to be horizontally and y is going to be vertically. But when it comes to like calculating the acceleration, the normal force and whatnot, it becomes a little bit tricky. So what you end up doing is you rotate the coordinate system, so you'll have a new xy plane, and we're just going to call it x prime and y prime, that is parallel to the surface of the ramp and perpendicular to the surface of the ramp. And that makes the calculation so much easier. And this is what it means by changing the bases. You're literally changing the coordinate system, going from horizontal to horizontal and vertically, to rotating it at some angle, which you probably guessed by now. You rotated by some angle theta to get your new xy coordinate system. And so the new bases will be x prime y prime, where x prime is equal to x cosine theta and then y prime is equal to y sine theta. And so this is one of the practical applications in which you need to change bases, because it makes the calculation so much easier, because as you know, the normal force will now be mg cosine theta. The acceleration the acceleration down the ramp would be, assuming it's completely frictionless, it's gonna be g sine theta. That's one of the reasons why changing bases is kind of important. It's important because it makes calculating things much more easier, and maybe probably in the foreseeable future you might be seeing what translation causes the xy coordinate system to rotate, and it doesn't like scale things up either vertically or horizontally. It just legit rotates. So I'm not sure if I'm gonna show you that. It might be in the linear shorts, but we'll see. Anyways, and that's pretty much it for change of bases. It's very short, but this is one of these lessons or topics that you have to work with examples a lot more to understand how to get them, and then at the same time representing, like, I want to represent it to you guys visually in the blackboard, so hopefully it'll give you like a better understanding or a better grasp of what changing of bases does. So now we're gonna move on to, well, not the Rank-Nullity Theorem, or not yet. We're gonna do a little bit of background information. Some of the stuff you might have remembered, or you probably learned when your kids were younger, and that'll be a row space, the column space, and the null space. So we're gonna start off with the column space, and so the column space is is the span of an m by 1 matrix, or m by 1 vectors that are in the columns of an m by n matrix A. There's also a subspace of Rm, and so that's pretty much it. In these next following definition, we're gonna be working with matrix A, which is an m by n matrix. So now the next thing we're gonna talk about is the row space, which it's the span of a 1 by n that are in the rows of A, and it is a subspace of R to the n. And then lastly, we're going to talk about the null space, or the kernel. That should ring a few bells, and it consists of n by 1 vectors x, such that a of x is equal to 0, and the subspace is R to the n. And notice how a row space and null space are both subspaces of R to the n. However, they are completely subspaces. As you can see in the row space, it spans a 1 by n matrix column. 1 by n. 1 by n. Row. Okay, yeah. It spans a 1 by n row matrix. And the null space consists of an n by 1 vector. So that they're completely different things. And so these are all important subspaces that we can read off of the matrix A when it's in row reduced echelon form. And so you're gonna probably be asking, like, how can you read this off, or like what happens when it's in row reduced echelon form? Because remember, um when you take a matrix A and put it in row reduced echelon form, a lot of things can change. It literally, and it's usually by means of row operations. If you remember back when we were working on determinants, doing row operation on a matrix literally changes the determinant by some value, and sometimes it may not even change it. So does row space, null space, and column space, do they get manipulated? Do they get changed? Is that something we have to keep our eye on? Well, the short answer is no. Row space and null space are unaffected when conducting row operation, and this is such a good thing. The reason is because we can find these subspaces, and so to find the row space, well, we simply need to, well, first we need to figure out what's the dimension of the row space. And so the dimension of the row space, it would be the same number of non-zero rows in the row reduced echelon form of that matrix. And then those non-zero rows are the vectors of the row space, or I guess the elements in the row space. So if you have a, not a 2 by 3, that's way too small, a 4 by 3 matrix, and when you put in row reduced echelon form, you have row 1 and row 2 that are non-zero. Well, the first row and the second row, well, it's 2, so that means the dimension is going to be 2 for the row space, but the first row and the second row, those are going to be in the row space of that vector, or not vector, matrix, my bad. Now, for the null space, well, it is also called the nullity, and it's the same way you found the kernel way back, like years ago, when you were working with matrices. So this should be something that you should be very familiar of, or you should just be able to do it in the back of, or in your sleep. So what about the column space? Well, column space is also a set of, it's the set of vectors B for which it's possible to solve AX is equal to B. And additionally, as I mentioned before, it also remains unaffected during row operations. And so to find the column space, well, again, we can use it by having the matrix in RR in row reduced echelon form, but we also need to use the original matrix to find the column space. And so, like, again, the first question poses is like, what is the dimension of this the subspace, or this, in this case, this column space? Well, the dimension of the column space is equal to the number of leading ones in the row reduced echelon form of the matrix. In other words, the number of pivots. And so once when you identify the columns that contain the leading ones, the vectors in the column space will be the same vectors in the original matrix. So again, let's go back to the, what is it? 4 by 3, 4 by 3, 4 by 3? Or is it 3 by 4? I think it was 3 by 4. 3 by 4 matrix. We put this in row, I think it was. Okay, you know what? Okay, 4 by 3 matrix. You put this in row reduced 3 by 4 matrix. Oh my gosh, 3 by 4 matrix. You put this in row reduced echelon form. You realize that there are two pivots, and the first pivot is in the first column, and the second pivot is in the third column. So now you go back to the original matrix, and the first column, that column of elements, that's gonna be one piece of your column space, and then the second one would be in the, which one did I say? Third column? Third column. I think it was third column. Can't remember. and I'll show you when we do the example, so it'll make much more sense. And so in short, it's the column space is the only one that you have to use both the row reduced echelon form version and the original form of the matrix. The kernel and the row space, you just use the just the row reduced echelon form of the matrix. Now we're gonna get into the interesting part, the Rank-Nullity Theorem. Now, when we find a row space and column space of a matrix, we will be able to see that the dimensions they're exactly equal to each other, and it makes sense when you put it in row reduced echelon form. The non-zero rows is in a row space, but at the same time, those non-zero rows will contain pivots, and those pivots is what determine the dimension of the column space. So if you have two rows, two non-zero rows, that means there has to be two pivots. So that means the dimension, or the dimension of the row space is equal to the dimension of the column space, because the number of pivots and non-zero rows are the same. So we will also see that it is equal to the rank of the matrix, because if you recall in one of my linear shorts video, it's gonna I'm gonna have a card pull up in case you didn't watch it. The rank it's just basically the number of non-zero terms in the row reduced echelon form. On the other hand, the dimension of the null space can give you a different number. It's sometimes, not all the times, it's not always the case. That's never biased towards this case or any other case, but there may be a chance where the dimension will also be the same as the dimension of the row space. But in other cases, it might be more than that. It might be less than that. It might be even zero. For all we know, it might be zero. And so now we're gonna present the theorem. So we're gonna let A be a matrix that is in dimension n by n. So that means the rank of A must also equal to the dimension of the row space of A, which is also equal to the dimension of the column space of A. Because like I made that little explanation like a couple seconds ago, and so when you add the rank of matrix A plus the nullity of matrix A, we should be able to get n, where n is the number of columns in matrix A. And that is very interesting. That is very interesting. And we're gonna show it. We're gonna show you. Well, I'm gonna be able to show you that this will be this will always happen with every single one of our examples. And this theorem, it has some consequences. Some very interesting consequences. So now we're gonna go back in time. Back when you were just infants, when we discuss about systems of linear equations. And so remember, we can express a system of linear equation with in matrix form, where we have the matrix A multiplied by the column vector of x, and then it's equal to another column vector. But we're going to consider those two different cases. So the first case is the homogeneous system, where it's equal to 0. And so here's what ends up happening. If the rank of A is equal to n, then that means the systems of linear equation only has a trivial solution, which is 0. That's all it means. So if the rank of A is equal to n, then there's the only solution there is. It's the trivial one, the where x is equal to 0. And then the null space of A consists only of the 0 vector. Now, if the rank of A is equal to R, such that R is less than n, which is the number of columns, the system has an infinite number of solutions, and it compromises in the null space of A. And if you remember on the examples that I did with systems of equations, I showed you one where it had one solution, another one that had no solution, and then infinite many solution. And that's pretty much the case where we had infinite many solution. We noticed that we had to incorporate the kernel. Now the only difference between what I have here and then the example is, in the example it was a non-homogeneous system, so that means it was not equal to 0. but we'll get to that later. And then lastly, if m is less than n, so that means there is more unknowns than equations, then the rank of A is at most m, so there must be a non-trivial solution. And then and additionally the dimension of that's supposed to be of, not if, of the null space should be at least n minus m. So in other words, if we have m being less than n, then that means when we put this in row reduced echelon form, we either have pivots all around, so from 0 to m, or we have one or one less, two less, three less, or just one pivot. And that's what I mean by the rank of A could be at most m. And then that also, the remaining things will also be part of the null space. So that's pretty much it for a homogeneous system. So now we're going to consider another case, a non-homogeneous linear system. In this case, where A of x is equal to a column vector B. Well, now this becomes interesting as well. So the system will have no solution if the rank is less than the augmented matrix of A augmented to B. Another way you could put this is if B is not in the column space of A. So if B is not in the column space of A, then there is no solution to the system. Now, if B is in the column space of A, that means there can be at least one solution of the system. And for the system to have one solution, the system will only have one solution if and only if the rank of A is equal to n. That's also making sure that the condition that B is in the column space is already met. And so if B is in the column space of A and the rank of A is equal to n, then the system has one solution. Now, if it has infinitely many solutions, well, again, it has to first meet the condition that B is in the column space of A, but also the rank of A must be less than the number of columns. And so that you just by looking at a system of linear equation, you can pretty much determine how many solutions are going to be there, and also what's going to end up happening. And so now we're gonna take another case again, so with systems of linear equations, but we're, aside from homogeneous and non-homogeneous, we're gonna now consider a case where A is a square matrix. And so what ends up happening when A is a square matrix, a bunch of conditions are gonna be true, and this will also hold true for its inverse. And so the first one is, well, the rank of A is gonna be equal to n. So if the rank of A is equal to n, then that means its nullity or the kernel is gonna be 0. And so the kernel, it's just only gonna contain the 0 vector. And what that also shows us is that the rows and columns will be linearly independent, as well as the row space and column space of A is going to be R of n, because the column and the rows are both the same thing, because the column is the number of rows, so there's gonna be R of n. And so now the rows and columns of A compromises the bases of R of n. And then the last couple of ones is going to be the ones that you've seen before, where the transpose of A is invertible, the determinant of A is not equal to 0, and the row reduced echelon form of A is the identity matrix. And so these conditions will also be true for the inverse of A. And obviously, back when we talked about inverses, A is A is A has an inverse if the determinant of A is not equal to 0. So that's pretty much it for this lecture. I apologize if this went a little bit too long. This was like a lot of information, but when we get to the examples, we're gonna see that it's really not that bad for the Rank-Nullity theorem, but for a change of bases, that it that really comes with how good I'm able to explain this, and then also how you're able to wrap around the idea around your head. Change of bases, I will admit, it's a topic that a lot of kids just kind of have difficulties wrapping their head around. And then the same thing goes with I believe like linear transformations. That's another one that's kids struggle on. And so that's pretty much it for this lecture, and I'll see you guys in the blackboard.